Okay, so we're going to start looking at Module 1, which is an introduction to technical drawing and AutoCAD. So since this is Monday, this is our first session. So Module 1, first session agenda. If I click on that, you're going to notice that we've done some of these things already, which are, in the realm of the course overview. So we're already done with that. And now we're ready to look at number 2 here, which is to look at those chapters in our book. Now, when I say read a chapter, I'm being loose with that. Okay. The chapters are kind of long. There's a lot of information in there, but the PowerPoints that I give you are going to be the main ideas that I want to make sure you use. So I encourage you to use the PowerPoints as your guide through the chapters for the things that are going to be most important that you want to pay attention to. Okay. So we're going to look first at Chapter 1, and this is out of your tech drawing book. Remember, there are 2 textbooks in this book, in this class. There's the tech drawing textbook, which is the hardcover kind of thick one. This is going to give us the concepts related to technical drawing, the standards, all that kind of stuff. And then there's the AutoCAD book. Okay, so we're going out of that tech drafting book or technical drawing book. All right, so this is my first PowerPoint presentation. And we're looking at Chapter 1. Now, as far as the objectives here, there's a number of different objectives, but we're really giving you an introduction to the design process and how mechanical designers, mechanical engineers fit into that. Okay, so I'm not going to read each one of these. So as we get to the start here, understanding the role of technical drawings. Technical drawings are the means of communication that we as designers and engineers have in order to let people in on the important things that need to happen in order for this to function properly in its end result. Sometimes it's on an individual part. We call that a detail drawing. And we need these details in order for when it gets into its assembly down the road, that it's going to fit and work properly. So the designer and the engineer are the people who are going to have that as their main responsibility. Okay. So these technical drawings are going to serve 3 main purposes. Okay. First of all, visualization. Okay. It's going to help us to understand, what does that part look like? So if I have a part in my hand and I have the drawing in front of me, the technical drawing, I should be able to match those 2 up and say that, yep, okay, they match. If they don't, then, we got to find which one is which. They serve as that communication tool. Okay. As I said earlier, this is the way that we let people know what are the requirements, what are the sizes, what are the tolerances, so that it can fit together properly, but also perform and function properly as well. I like to say that a technical drawing is probably one of the most important documents in a company. It really is, because that's where we define the requirements. If it's not fitting over there, now we're reworking. And anytime we have to rework something, what does that do? You're losing money, right? It takes more time to get it to where it needs to be. Time is money at a company. So if the drawing is right on the get-go, doesn't mean that mistakes aren't going to happen, but you want to try to have everything complete. You want to have the tolerances appropriate so that things fit down the line, so that you don't have to rework, so that you don't have to spend more time and money trying to get that to work. Okay. And then, like it says here, documentation. So it gives us that trail, if you would, because sometimes we even make revisions. Sometimes even if everything fit together, we might be like, oh, 2 years down the line, oh, we want to tweak this a little bit. And that part was used in previous assemblies. Now we're going to make a revision to it so that if it has to be made again, it's now to an updated level. So it serves as that documentation trail. Okay. So technical drawings, big responsibility of engineers and designers. And that's what we're going to work a lot on, not only in this class, but in that program. Wide variety of professions use technical drawings. So it's not just for our purposes in engineering, but as I said, it's that communication tool. So as we look out to where those drawings are going to go, they're going to go to quality department, because they have to check to see, are those parts okay before they go to the next place, right? They're going to go to manufacturing, the CNC programmers. I think I had a couple of those in here. They are going to be using those drawings in order to determine what are coordinates, what are the order of operations, how is this going to be set up on our machine. Welders are going to need that for their purposes as well. Like, what is the size of that weld bead, so that if it needs to be structurally sound, what is the size, the larger, the smaller, so that it's not going to fail in the in the field. Let me see here. Project management, fabrication, manufacturing, pattern making, construction engineering, landscape design uses technical drawings. So it's a really important document, no matter what industry that you're in. Okay. Now, stages of the design process. As designers and engineers, you are going to be probably front and center in each one of these steps. There are 4 main steps. There's problem identification, and this is where we clearly identify what is the end result or what is the goal of this process, or maybe even solving a problem, okay? Then we're going to go into ideation, and that's really where we start to develop concepts. And this is probably sketching. It's sketching out, hand sketching, whether it's on a piece of paper. Sometimes you hear about sketching on a napkin. Here's my idea. And it's kind of like figuring out what are the best, options maybe, and multiple options that could help us to solve our problem. Okay. Now, up here on our little flow chart, you're going to notice that we have problem identification, then it goes to ideation, and then it almost can go back up here, because what might happen is if you have a design team, you might have a couple people working on ideas or coming together, or you might have meetings and we're working things out, like thinking of different things. And then you kind of go back through and kind of do a loop here for a little while. And once you feel like you come up with 1 or 2 of the best solutions or the best things that are gonna fit that problem, now you're going to make a decision on what are the processes that we're going to need, or what are the elements or the features that we're going to be designing in. Okay. And then that's when we get to refinement and analysis. We usually pick one of those best ideas, and now we're going to be like refining it. We're going to be looking at, okay, now let's figure out what are the actual sizes. We're going to probably draw it up on CAD now instead of just a sketch on a piece of paper or a napkin. We're going to kind of, lay it out to see what our appropriate sizes are going to be. Might pick some materials. So we're going to be using CAD and such. Okay. And then we're going to analyze. So here again, you're going to notice that there's a loop here. So we kind of go through that process, because even here, we start to maybe introduce and look at, hey, if I make this part out of this material, can we make that on our milling machine here in the shop? Or do we have to send it out because the tolerances are more than what we have capabilities on, and we might have to grind it instead of, working with the milling machine capabilities that we have here? So, so maybe even refining, looking back and analyzing that to get to the point where we have the most manufacturable for the final process and function that we need. Okay. And then once we kind of get those things figured out, now we're going to implement and document. This is where we create the final set of working drawings, and we are going to release those to production, if you would, because now everybody's kind of had their ideas put into place. But the designer and the engineer, as you can see, are going to be like kind of the core of each one of these steps, because whether it's the ideas, whether it's the creating the documents, whether it's working on CAD, laying out, those are all going to be skills that you get to do in the future. Okay. So these are the 4 main steps of the design process. Now, concurrent engineering, I kind of alluded to this already, but concurrent engineering is a little bit different take on that design process, or the process that you go through in a company. A sequential process, which was, I'm going to say, very traditional, where you would basically get, your marching orders from marketing or sales got an order in, and they said, okay, this is what the customer wants. They hand it off to engineering, design it. Okay. And then engineering's like, okay, they pass it off to manufacturing after they've designed it. So they've got all their drawings made, they have everything done. And then manufacturing looks at it and is like, who designed this? What were they thinking? All right. Then it probably has to go back sometimes, but then it's manufacturing. And then you get to assembly, warehouse, maybe final product, and then it's sent out. So this is very traditional. And I'm not saying that this doesn't happen in industry nowadays, but more often than none, you still have those same departments, but now they're working in tandem. So instead of this being a handoff from one to the next in a sequence, now they're kind of working together. So let's say marketing gets a request from a customer. Instead of just handing it off and saying, this is what they want, they actually bring in engineering, manufacturing, and maybe packaging, final assembly to be there so that as the engineers are designing and coming up with their ideas, they're getting input from these other departments so that if you're getting input early on in the design process, it's not as costly to make changes as when it's after the fact and tooling has been made and things like that. Okay. And then there's lots of things that have to change. So concurrent engineering is kind of bringing together what we call a cross-functional team in order to be early on in that design process, right along with the engineers. The engineers are still going to have responsibilities to get the design in its final format and to document it, but they've gotten input from all those other places to then hopefully not have as many changes along the way because you've gotten, those stakeholders, if you would, that, know those departments the best. So concurrent process or concurrent engineering is very popular nowadays. Now, like I said, doesn't mean that it doesn't always go in this order, but a lot of times you're consulting with other departments in order to get there. Now, life cycle design, this is where we look at the design, not just to get it out the door and in the assembly and leave our facility. We're looking at serviceability. How long is that going to last? Okay, so making something maybe out of a certain metal as opposed to plastic so that it lasts 10 years instead of 5 years potentially might be, one of the things that is considered in the life cycle here. Might even have, as we look at after it's being used, can it be recycled? Do we make it out of recycled material so that it can maybe be reused and not wasted, where if you use certain plastics, that can't happen, okay? And then you're adding to the waste, out there. Also looking at how are we documenting this? Is this going to be paper that we're going to pass around and drawings that are on physical paper, or is it going to be CAD files that we're going to be working with so that we can go back later on and reuse these designs more easily and effectively? And that is the process that most all of companies are using nowadays. So all right. So computer-aided design and product development go hand in hand. Many times, like I said, besides, and even a lot of times, you're going to probably notice that you don't even see people hand sketch a whole lot. A lot of times, I know when I was working out in industry, I got good at CAD that it was almost faster for me to draw and develop on CAD than it was. And then I was already at that, what are my appropriate size level, as opposed to, sketching it out. But I'm not saying that that's not going to happen. If you're in a meeting and somebody doesn't have those skills, a lot of times that's the way it is. Now, CAD, computer-aided design, that is going to be the software that we use in order to create our parts, assemblies, and documentation. Okay. Then we've got another acronym, computer-aided engineering. Computer-aided engineering is going to then take those CAD models and parts and assemblies and put them into packages that are going to analyze. So things that are going to be like simulation software, looking at motion analysis, maybe looking at various temperatures, maybe load-bearing things, deflections. So it's kind of taking those initial models that were made in the CAD software and then putting them, down the road and using analysis on a computer. And then the other one that we have here is computer-aided manufacturing, or CAM. And this is going to be where, for instance, I think I heard, again, a couple people say that they were CNC programmers. You use CAM software in order to write the G code for machine tools in order to make sure that their tools are in the right place and put different features and such on individual parts in the right places. So using computers to create that sequence on a G code program for a CNC machine. Okay. Now, it starts with a CAD model. So as a designer, as an engineer, if you are creating that initial CAD model, it is so important that you have good geometry and integrity in that file. If you don't, okay, things like corners not meeting or overlapping, CAM software can't handle that. It gets really confused and it's like, can't do it. So it's really important. And that's one of the things that we teach here at WCTC is we teach you the good practices, the good construction. When you get into using parametric modeling like software or like SolidWorks software in your next course, if you continue on next term, things like fully defined models, stuff like that. So that when they are used in the computer-aided engineering and computer-aided manufacturing programs, you don't have problems. Okay. So it all starts here with CAD, and that's going to be something that you're going to get really good at. Designing quality into your products. So this we're kind of just touching on. This is looking at not only our part itself, but designing for Six Sigma. And this starts looking at designing so that your capabilities of the features that you are designing into it can be run on the machines that are in your facility. Okay. And that you are then able to make good parts all the time. Okay. So I'm not going to spend a lot of time here because this is just a little sliver, but designing for Six Sigma, and then also going through what we call the DMAIC process, where you go through define, measure, analyze, improve, and control. Those who live in that quality world, this is really familiar. Now, the next section here in our book goes into detail with this design process, and it uses this bike company as an example. It's interesting. I think it's good, but I'm not going to spend all the time here. It's kind of like hitting, and what's nice about this process, and I encourage you to look through it and read it in detail, especially if you're interested in bikes and suspension design, but it walks through each one of these steps in the design phase, like problem identification, and it's using this as if you would a case study. And then it goes into ideation and the process that they went through to kind of come up with their ideas as a team of how they're going to approach this. Okay. And then they look at, okay, we're going to make a decision on what design we're going to go forward with. So they select then the best design based on the ideations that they had earlier. And then they run some data through prototyping to see how it's going to perform. And they continue to or here's an example of the prototype. Prototypes are usually not made out of the exact materials that are going to be the finals, but they give you a good working example. What's nice about prototyping is, as you can see here, some of the elements are going to be the same, but maybe some of the new elements, like I said, maybe they're 3D printed, or maybe they're modeled using wood sometimes, so that you just can get an idea of how things are going to, maybe work in their final form. And then the actual design phase refinement. This is where we're going to be looking at things like weight, strength, cost, optimizing, making sure that it's manufacturable, making sure that parts are available. Okay. Sometimes as a designer, we need to consider those purchased parts and where they're being sourced from and how long it's going to take to get there and how much they're going to cost. Sometimes cheapest isn't always better. Sometimes cheapest has to come from China and has to make a boat to get over here. And if you need a bearing within, a day or two, it's a little harder to get it. So a lot of different variables go into, looking at this refinement stage. And one of those is how available are the parts. Here's analysis. This is where we can look at it on a computer, but then also through the prototype and see where there might be stress concentrations, where we might have to put more material or different materials for it to perform better. Finite element analysis is one of those simulations where we can run it through a computer analysis, and it can give us red is going to be like where you have high stresses, and then the cooler colors, if you would, are where you're not going to have, as high of stresses. So now if you look at this model where we see the red on this suspension on this particular part, this is going to be an area that you want to pay special attention to, whether it's making it thicker or changing the angles and maybe changing that design, then re-putting it through the what we call FEA analysis, finite element analysis, and see if we can get those colors to be cooler. Okay, meaning not red, right? So it's a really nice visual. Then you've got one thing that they say in this, and I thought it was really kind of cool and interesting, was that this bike company, all of the people who work there are bike enthusiasts. So they bike to and from work every day, or they're biking in, different types of competitions. So the people who are working, engineering, purchasing, marketing, they are all like intimate with the bike. And so I think that's really cool when you can get a cross section of people who are invested. So I think that was unique about this particular example. Then it talks about more of that design process, design selection, again, looking at, alternatives. And it's kind of like that looping effect, kind of going through and refining. And then it's implementation. So now we're seeing where they're, bringing together the materials that will probably be the final materials. And then how are we going to do this? You can see that we see some welds in this case. Maybe we're going to be casting, and such. The documentation, this is where we create those drawings, whether it's a technical drawing of an individual part or an assembly of how things are going to go together. Those are going to be part of that documentation process. Prototyping, kind of going back to, reevaluating the designs. And then the other thing that it talked about here was creative techniques. And this is where you don't have to be the person with all the good ideas, okay? When you are designing out an industry, you have departments, you have, like I said, cross-functional teams that are going to give you input. So sometimes I think people think that if I want to be a mechanical designer, I've got to come up with all the good ideas. No. You're going to have good ideas based on your experiences, but that doesn't mean that you have to solve the full problem. You're going to have other people around you, in order to do that. So in here, they talk about brainstorming and other different, things that you can do, doing research on patents and looking at getting ideas that way. More creative ideas. And then product definition. So once we have everything all done, how do we capture what we did? And that's usually going to be through, and you'll notice that central to all of these things are the CAD models. And that's the responsibility of the mechanical designer, the mechanical engineer that is working on that project or product. So what the processes are going to be dictated by tolerances and the features that you specify on that part. You're going to have data analysis. You're probably going to have, that captured in some way, some form in a computer, process or in a computer model. What the finishes are going to be, the materials, the list of parts on the bill of material for the final assembly, the history of the revisions. Those are all going to be on the CAD model. Okay. So that's why, like I said, I can't emphasize enough. When you create a drawing, when you create a design, when you release something to production, one of the most important jobs and one of the most important documents really in a company. If they're going to be looking at saving money or reducing cost, they start with that drawing and they start looking at, do I need 3 decimal places here or can we get by with 2? Can we open that up? Because smaller the tolerance, we're going to find out, the longer it takes to make something. It's a smaller target to hit. Can we make that wider? Can we put it on a less capable machine that doesn't cost as much? So that all starts here. So you've got a lot of responsibility, but it's really exciting. And then it shows at the end here, like a design portfolio. We won't worry about that necessarily in this class, but when you get to your final course in both the mechanical design and the mechanical engineering technology program classes, we have what we call a capstone, and you will be capturing a portfolio for a design that you do with a group of fellow students. So that takes us to kind of the highlights of Chapter 1. Okay, so I am going to stop our recording here.